6 minutes looks good. Hi and welcome. Welcome to the newest installment of the Square Brainfood Talks. This is the format where regularly on Fridays for lunchtime, we give you valuable insight into the topics that are related to software engineering and that not only fascinate us, but also are part of what we work on a daily basis. Today, we have the pleasure of hosting another talk on software architecture. In just a moment, senior developers Raphael and Paul will start the presentation about why they don't think that distributed systems have to be difficult. Please, afterwards, we are going to have a Q&A session. So please, if you have any questions, put them here in the chat and I will hand them over after the talk to both guys, and we will try to get out as much as possible for you at home. So without further ado, please, Paul and Raphael.
Thank you, Lorenz. Thank you very much. We are very excited to have the opportunity to talk about why we think that distributed systems don't need to be complicated and why we love actors, by the way. As you see, we are two of us today. My name is Paul. I'm a software gardener here at Square Solutions Vienna with a strong focus on maintainability, testing, and quality. And I have the pleasure to have my colleague at the side, and this is Raphael. So please, Raphael, introduce yourself.
Welcome, also warm welcome from my side. My name is Raphael Rehberger. I'm a software developer at Fronius International, today joining my colleagues here in Vienna. I'm a floss enthusiast, so everything that is free, open source, and Libre, this is my world. And I also do enjoy designing architectures and everything that has to do with service design. And this is, I guess, also the reason why we came to this talk today. We are talking about actors, and I would like to deep dive a little bit into the history of how we came here. And with that, I want to go back into the year 1973, because this is the time where we actually started to think about distribution the first time in computer science. So the thing is, if you want to get the picture, you have to see these things. We had everything already there, as we know it today in computer science. However, everything was a lot more clunky and bigger than we know it today. We have a storage cluster here with approximately 280 megabytes of disk size, which is huge. Also, we have this 1 kilobyte of RAM block, which is only 1 kilobyte, and the size is also quite big. But aside to that, we had a very interesting development around microprocessors. Microprocessors became more popular back then. And with the popularization of microprocessors, we also went into the direction of distributing things from each other. So each small microprocessor took care of handling a single responsibility of a system. And with that, people were challenged to figure out solutions around it, even back in the year 1973. And this is the man we're talking about today, or at least the concept of this man we're talking about today. This is Carl Hewitt, and Carl Hewitt in the year 1973 described the paper A Universal Modular Actor Formalism for Artificial Intelligence. Basically, a paper describing the actors and how they are going to work. But I guess enough of the history, time to hand over to a little bit more introduction about of the actors.
When we're thinking about some of the challenges that we have with distributed systems, one of the challenge is the concurrency of incoming messages. So if you have a system where several clients are sending messages to, the system, of course, cannot see and predict in what order or at what timing the messages arrive. So usually that puts a lot of stress to the system because you have to deal with this. So for example, with multi-threading and all the problems that we have doing a multi-threaded system. One of the solutions to this could be, for example, to put a queue in between. So that means the messages still come in a concurrent manner, but to the queue, they get a specific order there, and then the system on the other side can dequeue the messages as it likes to do. It can be still multi-threaded, but it has all the opportunities there. And if you scale it down on a pretty smaller level, then you basically get one of the benefits that you have when you're talking about an actor. So an actor can be seen as a small unit in a program with a queue, a so-called inbox attached to it. And so the concurrently incoming messages are queued in this inbox, and then, and that's important, the actor usually uses these messages in the inbox one by one. So it does a sequential execution with a huge benefit in the implementation model of the actor system, because you do not have to care about multi-threading, you do not have to care about locks and such things. So there is a really way easier way to implement such an actor. As a concept, an actor consists of three things. One of the things is the identity. So the identity means it consists of a type. So what is it? In our example, it could be a user actor and another attached tag to it. So for example, it could be the user David@Square.at. That could be one of the identities. And with that, it is possible to even have multiple actors from the user type or multiple actors for David@Square.at, because the combination is it. And then, of course, the important part is the behavior. So what does the actor do with the incoming messages? And there you, depending on the system and the language that you choose and the platform, you can do your usual object-oriented or functional programming on the side. And optionally, it could be that the actor also maintains some kind of state. That could be an in-memory state or a state that is even persisted. And that gives this actor the possibility to even know something about its past. But that is optional and that doesn't have to be this way. Now you may ask, but how do you then distribute load? Because if you have a single-threaded environment, it could be, and you have a high CPU-bound activity, it could be that it's not enough to have just a single thread. Or, and this is the thing that we are doing here, you are it is very easy in an actor-based system to spawn out even more actors. And the actor framework around it does all the heavy lifting. So everything about instantiation and stuff. So actor frameworks usually manage a lot of things. So for example, the lifetime of the actor, when does it get become to life? When does it get terminated? It manages the inboxes of the actors. It cares about consistency. It cares about very important things about message delivery, such as error propagation, and even does it across processes, across different worlds, so across different data centers, for example. Yes, a few things about the messaging patterns that we usually see with actors. Before diving too much into that, we have to step a little back and take care to understand that we see what an actor actually can do. Basically, it boils down to those three things. It can create another actor, so to send messages to another actor. It then can send the messages, and sometimes it can decide to dispose or terminate the actor. The details depend, of course, on the implementation and the actor framework, but basically, these are the three things of this actor concept. So if you take a look at creating other actors, if you think of an actor as an entity to perform some task, this task can be pretty huge. And the thing with an actor-based system would then be not to make the actor bigger and bigger and bigger and introduce multi-threading, but to fan out the work to other actors. And those actors, as for example, the green one in this example, can then even add more actors and distribute the work even further. And this makes it possible to have actors that are pretty focused to a single responsibility and delegate all the rest of the work that has to be done to other actors. The disposition and termination of actors can be done either by the actor itself, so it can tell the actor framework, hey, usually I do not expect any more messages in the next time, so please get rid of my resources, or it can just stay around, and when the actor framework decides it has some kind of memory pressure, for example, it can decide to terminate one of those actors. Yes, how does the message sending work? So if you talk about a distributed system with a lot of infrastructure in between, with a lot of network hubs in between, there can be a lot of things happening when we are talking from one network system to another system. So for example, when we are sending messages, such messages cannot arrive, or they can arrive, but we do not know that they have arrived. So there are a lot of things that could happen. And the question is now usually, okay, how to deal with this situation. So if we know that message did not arrive, do we just drop it and say, okay, don't care, it has happened? Or do we retry it? And even how to decide, how long do we wait until we decide, okay, this message seems to have dropped. So there are a lot of things that have to be considered. And this is also one of the strengths where the actor frameworks can help. If we are talking on a more higher level, there are two basic modes of communication. One mode is called the tell mode. So this is the version where you say, okay, I have to distribute some work to another actor, I have to send a message, but I do not really care what the actor that I call really does. So I do not need anything from it. And this is the tell. So this is sometimes also called the fire and forget mode. The other way is that I ask the other actor to do something and tell me about it again back, so that I get some answer, I get a response, at least that it has already happened. And this is usually what we know as the request and response pattern. Okay, so if we talked about these basics, let's take a look how that looks in reality.
Yeah, so now that we know the basics and now that we have a good introduction into how actors work, I think it's time to get a little bit more hands-on, or at least as hands-on as we can get here. So we're going to model a very simple IoT device, or more or less two simple IoT devices. Imagine the following situation. We have two devices, a humidity measurement device, a so-called hygrometer that is capable of measuring the percentage of humidity in air. And then we have an acting device that is an air humidifier. You see it in the bottom right side, where this device's purpose is to vaporize water to effectively increase the humidity in air. And when we model this control loop, we could design it like this. So at the bottom here, you see these physical devices. So we have the hygrometer, as we just said, and we have the air humidifier. And our physical device of the hygrometer is supposed to be sending measurements of the humidity to our hygrometer actor. And the blue box that you see here is supposed to model the actor. And we tend to model these things as digital twins. Digital twins are just virtual replications of the real devices in this regard. So we have a digital twin wrapping around the actual hygrometer as a physical device. And now our hygrometer is sending messages to our hygrometer actor. And this actor is going to decide what to do with it. So based on these measurements that are incoming, this hygrometer actor could decide that it needs to activate the air humidifier because, for example, the air humidity is just too low. And one possibility to do this, as we've already learned, is through telling. So what this actor then will do is put a message with a control to the humidifier. The humidifier actor will pick it up and then takes care with the communication to the actual physical device that is in the field. Optionally, of course, this device could report back status. And if it did that, because I guess in this example here, it's kind of out of scope, we could also respond back to the original hygrometer actor with an acknowledge. For example, the operation worked, we actually humidified certain milliliters of water. So now let's deep dive into the code. And for the example that I've brought here, we are using Akka. Akka.NET or Akka per se is a framework that is very popular in the Java and Scala world. And it's basically the go-to framework that you're using when you want to use actors in Java. So what do we start with? We are modeling a very simple POJO, the hygrometer message. It is very simple because this is the thing that the actual physical device is supposed to be sending to the hygrometer grain. And it just wraps a single POJO with a single object in there. It's a humidity in percent. Then we continue on to model the actual actor. And the first thing that we see here is when we create our class. So from the class signature of the hygrometer actor, we can see that we extend from an abstract behavior that handles a humidity measurement. And as Paul already mentioned, we have two entities now in our actor. We have one part that is sequentially running based on the message that is incoming, and then we have the queue or the FIFO that is actually holding the message. And from line 3 to line 5 here, what we're doing is we're binding the actual implementation of the sequentially running code to the FIFO. And if a message lands in the FIFO with the type humidity measurement, then the actor framework makes sure to deliver it to the callback provided here. So in this case, it is the on measurement function. And for the sake of simplicity, this function does only log right now. But of course, we could implement here the delegation to the air humidifier. Then let's continue on with our second component in the system, the actual air humidifier. And here we once again model a POJO. So the first thing that we would like to see here is, of course, some kind of control to the air humidifier. And in this case, it's the float that is modeling the milliliters of water that need to be evaporated. So as an acting operation. And the second thing that might be interesting here is the actor reference. So the sender of this message is supposed to enter the reference to itself. So it basically is passing a self-reference into the message that is sent. With this, later on, the humidifier can actually respond back to, because the reference is encoded in the message. And then finally, if our air humidifier, for example, finished the job, it could respond back to the calling actor, the humidifier, that the operation per se was successful. And now to the final part of this cool example, is the actual actor of the air humidifier. Once again, we implement an abstract behavior of handling air humidifier controls. Once again, we do handle the binding to the queue with managing the control type. So here we have the air humidifier control. And if the queue contains such an element, then it delegates it to the on control function. And here we perform the actual vaporization, or at least this actor takes care of sending it to the physical device in the field. And depending on the result of that, we can now access the control source, so basically the calling actor, by telling him the result. And here, for example, we just sent back the operation that had been sent to the actual device in the field. So with that, I just want to give you a little bit room for thinking. Doesn't that look very suspiciously object-oriented? Isn't it very modeling-wise like object orientation? Also, do you think that the CQS pattern slightly resembles the messaging that we do here? So, and with that, we can now kind of tackle a more complicated topic. How can we model systems of actors? And one of the very typical patterns on how to do it is with these 3 layers. So here in the center, we have our system of actors. So we have really very small blocks of actors that are supposed to handle a single smallest possible function. They can be interconnected however they want to be. So that's basically up to you as a developer on how you make the message flow. The rule of thumb, of course, is make it simple, keep them small. And now to interact with the rest of the world, we usually also have some kind of front ends, because direct actor messaging might not be the thing your browser likes to do. So we might have some front ends in between, something like REST APIs, API gateways, some web applications, or even microservices that could utilize system of actors. And on the right side, we see that our actors can also perform something. They could, for example, perform a storage operation. They could cache something in Redis. They could cache something in a database eventually, or just simply persisting something to disk. And with this, we get into the direction of thinking a little bit about concurrency. So when we use an actor system, then using concurrency is basically implied by the model. And now the question is, how do we achieve concurrency in such a model? So just a quick recap again. Messaging is done through FIFO queues, so through the inboxes of the actors. And we have to make sure that the actor can only pick up a single message at a time. The messages are additionally passed by value, and also they should be immutable. And one of the biggest things is that the execution of the actor itself should be or must be sequential. With this, we have to restrict ourselves to not use any kind of threading or multiprocessing. And if we spin this thought further, we also prevent global shared state. You know, this is the thing that most of the developers are arch enemy. So actors luckily prevent this. So the only way we actually can share state with actors is through messaging. And then we have to lean back and think a little bit about the implications. We don't have any guarantee of message ordering. So we do not know anything about the queue, which messages are already in there. Same thing, we don't have any guarantee about an immediate answer. So if the queue of that actor is full, then of course it might take a little bit longer, in contrast to if the queue is completely empty. So with that, we have tackled basically the obvious things. Global shared state is bad. But if we go a little deeper into the actor itself, then we can think about holding state in the actor itself. And here comes the cool thing, actors are single-threaded. Therefore, if we hold state in an actor, we can safely access it. Due to the synchronous execution, we prevent any kind of race conditions. But nonetheless, we still have to ask the questions, do we really need this? And what exactly happens if the cache is empty or if the state is empty that is stored inside the actor? And what happens, for example, if my actor crashes? Can the actor handle the case where we don't have any state in there? So those are some things that you need to consider when designing it. And now we get into the direction of resiliency. How can we achieve resiliency in such a system? As we already said, most of the things happen on the queue level. Actors are just the part that get attached to the queues. And if we think a little bit about this, then all of the state that lies in a system of actors is in reality in the queues that are bound into that actor system. And now imagine we would have an actor framework that is capable of providing us a mechanism to persist everything that is stored inside the queues. With that, we effectively get the possibility to snapshot our queues, to have pictures in time of the whole system. And this gives us the possibility to start, stop the system every time we want. We can continue from these states. And one of the positive side effects is also that we can just draw a snapshot from production and move it into our development environment. Would be a very simple thing, would be very effective. And with that, we need also to compare microservices versus actors. So you probably all had these questions right now. Isn't that very familiar? Isn't that very similar to microservice? What's the real difference here? And I think when we tackle it on a side-by-side basis, the best explanation for a microservice is that it is just an implementation to distribute functionality. Whereas in actors, we're coming more from the mathematical side of things. So here we try to have a provable model that allows concurrent computations in general. We try to move all microservices into a single bounded context, or other put, a single bounded context is supposed to model a single microservice. Whereas in the actor world, we try to once again go a little bit lower. We try to make it smaller, and we try to model the smallest, most granular functionality into a single actor. Also, that brings us benefits when we think about scaling. Both are scaled vertically, yes, but in microservices, we typically scale in a multi-process manner. So for example, in Kubernetes, we just spin up another replica. So it is another process that we spawn up. In the actor scenario, we of course also can scale vertically, but we do it slightly different. So instead of really focusing on the number of processes that are hosting something like an actor, we really try to think more about the direction, where do I put my actor? Does the machine where I try to put my actor or where I try to instantiate my actor has enough resources left? From a coupling perspective, this is pretty much the thing that they share. So both try to follow a loosely coupled architecture. However, actors just go one level deeper again. So we try to model the functionality in an architecture of actors on a very small level. And here we come to the last point here in the direct comparison. For microservices, we always try to have a single domain for a single service. And in the actors, once again, to just phrase how important it is that an actor is small, we just take the single sub-problem for a single actor. And when we talk about microservice design and the architectures, we have a typical pattern in microservices. So we typically follow something like the N-tier layer. Like the example here on the left, we have our 3 layers. Where in the actor systems, we try to go in a very radical approach. So we don't impose any kind of layering. We have a completely weakly coupled system without any restrictions in the terms of how can layers communicate with each other. This allows us as developers to make a very flexible wiring and a very flexible communication between actors in such a system. Of course, we have to be aware that things like cyclic messaging are problematic, but nonetheless, we are very flexible. And when you start out working with this flexibility, you will usually start to abuse it at the beginning. And one of the must examples that you as a starter in the actor world will potentially run into is the hot node thematic. Let me explain you what that effectively means. So on the left side, we see sender actors. Those are, for example, triggered every millisecond and produce a message or due to user loads. And then we have a single receiver actor. Now, if the load on the left side becomes too big, you potentially can think about what's going to happen. Remember, there's a queue in there. So the queue will fill up. And if the receiver actor is too slow to process the queue, then at some point you will eventually run into a memory limit. It's the definition of a hot node. But luckily, we have tools in place to prevent exactly these things. And coincidentally, that's also how we scale in actor systems. So here we have the same example, more or less, but instead of pushing the messages to a single receiver, we instantiate multiple receivers, one for each of the senders. Because we can easily do this, as Paul already mentioned, the only component that is necessary to identify this actor is the type of the actor and the address of it. So with that, we can just easily spawn the same functionality with a new identity. Right. And now, when we have this in mind, you might say, hey, but isn't this a very bad idea to just dumbly put lots of actors into place? And the answer is just simply no. If we once again compare the microservice versus actor thing, when you try to model something in a microservice and you spawn an additional microservice, things like scaling up the replica count once again, you immediately have 80 megabytes of additional RAM usage, which is quite big if you think about a very lightweight actor instantiation that potentially takes less than a kilobyte of RAM. In the microservices world, we also have to run the services all the time. So if a service goes down, well, we potentially have it not reachable anymore, and the system might not work anymore. In the case of an actor system, the actor takes care on instantiation of the actors, and therefore we can also dumbly dispose it whenever we need it. Load balancing is another topic. Here, addressing is the key in the actor world. And for service discovery in the microservice world, we just lean back in the actor system and let the framework do the heavy lifting for us. And now, the last part, when we go into the direction of making things small, we have to learn about the term nanoservice. So the idea is a microservice has just too much functionality, and we need to make it smaller. And the obvious thing is a nanoservice then. And here are some guidelines on how you can make the actor as small as possible while still being sensible. One of the good things is, I guess, the lines of code as a metric. So try to keep the lines of code as little as possible. Because the more lines of code are in there, of course, the more functionality will be in that actor. And if you try to stick around the 50 lines of code limit, you're probably good. Then, when you design the actors, it's very important that you design them deterministically. That means that the same message at the input of the actor produces eventually the same output. Also, if you have any kind of long-running operations, try to separate it. Try to follow the divide and conquer approach. And the same thing, of course, for parallelizable operations. Now let's jump into the topic of virtual actors.
Okay, thank you. When we're talking about virtual actors, this is a notion that was introduced by a framework called Microsoft Orleans, and this is a cross-platform framework for distributed scalable application based on such virtual actors. So what does then the actual mean? If you think of virtual actors, you can think of the term virtual as in virtual memory. So virtual actors exist all the time, but they might not be instantiated at all the time. And Orleans, in this case, then takes care about the instantiation. That's what we call the activation on demand. So if a message gets sent to an actor, it will be there. And Orleans cares about that it is really available for communication. So a little bit more of Orleans nomenclature. The grains can be combined into a so-called silo. That is basically a process where a lot of grains can be executed. And many of those silos can build up a cluster. And even there could be more, so it's absolutely possible to have multi-cluster scenarios. When you think of the grain life cycle, it's basically like this. So if you send the first message to a grain, then Olean says, okay, we do not have it already in memory, so it activates the grain. Then the grain is active in memory, it processes its messages, and eventually it gets deactivated. And if there is some state to be persisted, the grain, in conjunction with Oleans, also takes care of the persistence. And then the grain does not consume any resources in memory anymore. And if the next message arrives, then Oleans can then reinstantiate the grain, including its persisted state. And so the grain can just continue where it left off. Another thing is location transparency. As you saw, a grain system can be pretty large. And it is nice that the client that calls a message, that sends a message to a grain, does not have to care about where the grain actually is instantiated, so where the code is actually running. So in that case, for example, we see a green grain that is sitting in the same silo, so that is a pretty short path, but we could have grains in other silos, and the silos could even be very distant, so they could be basically in a data center on the other side of the world. And still, Oleans, as the management system of all the grain messaging, takes care of this. And besides of some network latency topics, of course, the client must and will not know where the grain actually is running. And that gives us a very great power of flexibility. So then let's take a look how our hygrometer sample would look like in Oleans.
Wonderful. Yes. Now with that in place, we just have to remember back to our hygrometer example. And we try to model the same thing again, but this time in Oleans. And the first thing we're starting with is interface work. So as you see here, we have the first interface is the hygrometer grain. And it inherits from the I grains with string key. With the grains with string key, we essentially say, how can we address the grain? And that grain in this case can be addressed with a string. The string can be passed by the caller more or less. And we implement a single function. That is to receive a measurement. That obviously also takes only a single parameter. It is the measurement. And what you might notice here is that it returns a task. And the reason for this is that Oleans enforces the function signature to be asynchronous. Why is that the case? Because under the hood, as we already heard, we don't know where the actual implementation lies. Could be in a cluster in New York, could be in a cluster here in Vienna. Nobody knows. And exactly for this, we have to think about asynchronous I/O. There will be a lot of blocking I/O if we would make it synchronously. And that's exactly why Oleans basically enforces asynchronous development by default. And now, this is the interface of our hygrometer. But we also had a second component in our system, the air humidifier. And once again, we model a simple interface. We once again address it with string keys. And this time, we see the handle control function. The handle control function on the one side takes a single parameter, the control. So what has the air humidifier to do? And then it returns a result, the result of the vaporization eventually. And with that, let's jump into the actual implementation of this hygrometer grain. So we just implement from that interface, and then we create the implementation for the receive measurement function. The first thing that we see is that we get the primary key of the grain. What we get from this is the identifier of the grain we're currently in. So the name or the address of the hygrometer grain we're currently executed in. Then we need to get an address of the air humidifier grain that is actually capable of performing the operation we wanted to do. With this, we just use our same address. If it doesn't exist, it gets instantiated by the actor framework by itself. Then we just figure out what we want to do. So we take the measurement, analyze it, and see what we have to do. How many milliliters of water do we need to vaporize? And then we just simply message the handle control function with the control. We can nicely await it, like we would in any other implementation, and check the result, just in one execution. Right. And with that, I would like to tackle the obvious topic when not to use actor-based systems.
Because when two guys are really excited about a thing, you have to be really aware where are the limits and where might be not a good case to use. So to be clear, actor-based systems are obviously not the solution to every problem, but I think they should be worth considering it. Sorry, too fast. And so this brings us here to some situations where actors might not shine too bright. So if you, for example, have to move a lot of data between two parties of a system, then you have to be aware that all the messaging gets via a network connection, and so the messages have to be serialized and deserialized, so putting a lot of data via that might not be the best idea. If you need shared memory, that's not happening here, and see it as a good thing. Of course, if you have problems that are hard to parallelize, or if you have a lot of complex logic where you want to have some multi-threaded magic going on, basically that's not the thing where this shines. And of course, of the many network calls that you might have in between, also some reaction time guarantees cannot be really given. And at the last state, as Rafi also showed in his example, if you really need global coordination and waiting points where things have to wait on each other, that's probably not the best idea to use this in an actor-based framework. But of course, there are things where it's really a good idea to consider using an actor-based framework. And what is a basic structure where it's really great, that is, if you have really many loosely coupled entities, as in this example. So what does many mean? Many could even mean for each human in the world, you have an actor. So you could have and totally implement a system with billions of actors, as long as not many of those actors are instantiated at the same point in time, of course. So, and if you don't have to wait on each other, then it's a good idea, and it's totally fine to really have lot of actors in place in your system. That's totally possible. But the question now is it just a thing for really big systems? So on the right, globally distributed system running in several data centers? And I would say no. This is, of course, the thing where it's really super powerful and helpful, but even on the other side of the scale, so if you think of a single process console application, for example, it could be totally worth considering using an actor-based system at the core of this single process. Usually your system will probably be somewhere in the scale in between. And what actors give you is a great way to be elastic and react to all the scaling demands that you see in your system. That could be scaling due to domain demands, so that your system must fulfill more and more different use cases, for example, and it could even be at runtime. So if at runtime the system really scales, because maybe in an IoT scenario, if you have to support more and more devices out there, then it could be a really good idea to easily scale the system using an actor-based backend. So let me give you an example. Let's say we are operating a lot of devices, of physical devices that are somehow distributed along the globe. And as you see here, we have very old devices like the Model A with a firmware version of 26, so it's pretty often updated. And there's the new shiny Model X that has maybe someone with the very initial firmware version X1, and there's another one that has already the more recent firmware version. But now the goal is to update the firmware of some or maybe all of the versions of the devices that are out there. And if you have to tackle this problem, you have to be aware of some things. One thing is updating the firmware of a physical device might take the device offline for a few seconds, for a few minutes, depending on the device. But on the other side, you usually want to have the whole system, so the global spanning system, operable at the same time. So having some devices offline might be cool, as long as the majority of the other devices are fine. So it's not possible to really do a global simultaneous update, because that will take the whole global system down. And here is really a thing where actors can shine, because what you then usually can do here is to provide so-called digital twins A digital twin in that case is an actor that is mirroring the physical device that we have out there and be a representation within our software system. So this actor can know about the location of the system, the model number, about the firmware number, about measurements, what else is the capability of the device. And with that, we can then interact from a higher level of the system with those actors, with those digital twins to operate the devices out there in the field. And the flexibility to spawn even more actors as we need gives us the possibility to make a different kind of partitioning here. So for example, you could think of partition it by region. So update all the devices here in Vienna or in Central Europe, whatever. You can do it by time zone. So for example, if you have a device that is just operating during sunlight, it can be a good idea to update them by night because then nobody would care usually. Or you can say, I just want to update all the very old devices because we have some security issue there. Or we can say we have a specific issue in firmware version X26 and we have to update those versions. Or it gives also the possibility to say, let's take all the devices in a single building, for example, and treat them as a single virtual device and operate them on that level. So you have a really very flexible system how to see your system. Yes, and in that case, let me just show you an example as a use case that could be here important. How does the reporting of the progress look like? And in this example, we have a pretty simple layering. So we have at the bottom, we have the digital twins where each device is a grain. And here in this example, we decided to make a grouping by model. So all the model A, for example, are reporting to a single grain up there. And they can report the progress. On the grouping level, the grain can then aggregate the information and report it even higher to a higher system until we reach our dashboard or whatever we want to have it. And this flexibility can be also used to cut it in more levels or in different shapes, so as the problem supposes it to do. So let me give some final message to you. Actors are a tool, and I would say a cool tool, of course. But I think where you can consider using it. So for example, if you have a microservice system and your domain grows, you have to fulfill more business requirements, and that would mean to even introduce more microservices, and maybe you also have some problems operating your 4 microservices. You might be not very happy about this. And so if you fear this added complexity, it might be an idea to consider using actors instead. Or on the other side, if you have microservice that does too much, where you see, oh, if we have cut it differently, it would be more helpful. But again, you're fearing the additional complexity you get out of there. Maybe consider using actors because the slicing and cutting is way easier with this system because all the heavy lifting of the messaging between the services is done by the actor framework. Okay, so here we are at the end of our talk. So we say thank you for listening, for your interest. And we want to give a heads up on the next upcoming Brainfood Talk. Our lovely colleague Lorenz will be talking about modern Angular development. And with this, I have give back to Lorenz for the Q&A session. Thank you.
Okay. Thanks a lot, Paul and Raphael, for this very fascinating talk, and also the comparison between Akka and the Orleans implementation was very interesting. We still have about 15 minutes, so if anybody has questions, please still continue posting them in the chat. So from what we have here, we first had a little exchange, which I think can be summarized by Alexander Wollmann's last entry, which was, I'm trying to understand the difference between serverless functions and actors. Message queues seem to be a similarity.
Okay, if I understand it correctly, what Alexander mentions is that if we would use a serverless function and a queue attached to it, that would be basically what we described here as an actor. Yes and no. So yes, for the yes part, I would say exactly structural wise, we have this, but we just have then one actor. And the power of the system is that we have an active framework around it that really cares about all the heavy lifting of the communication, of the instantiating, of persistence, for example, that are also all, or some of those, especially persistence, for example, is a thing you really have to take care of yourself if you use just the serverless function. Of course, the spawning up of additional instances can be done with serverless functions as well. But the partitioning, not only to distribute load, but also to distribute parts of your algorithm, so of the business requirements that you have, is still a thing where you have to deploy a new version of the, or an additional serverless function to really have the opportunity to use that. And with an actor-based system, it's way easier. So in both directions, so also on the scale level and on the business implementation level, so on the algorithm level, so to say, to scale it in both directions very easily. Yeah. So, do you want to add something?
No, that was a perfect explanation, and I think the.
Thank you very much.
Cool. So, Alexander, I hope that answered your question. If you have any follow-up on that, please feel free to post it in the chat. Next, we had a question from a user JM Lero or something in that vein, who asked, what would be the best way to change or update a message format in case a feature is added in an actor, and how to then support backwards compatibility if required?
So that's a very good question. And in general, this is something that the actor framework can take care of. So there's the possibility to implement versioning like we would do for simple HTTP APIs. We would be able to support multiple versions of the same grain type or of the same logic, more or less, in the same system. And with this, we can decide on the caller side which version I do prefer. So we have all the flexibility that we would have already with simple versioning. Hope that answers the question.
Maybe to add up here, what you could even then consider doing is putting all the version 1 grains, in Orleans case, in one silo and all the other versions in another silo if you don't have other considerations regarding scaling, for example. That could even make it easier because you're still transparent, so the caller doesn't need to know exactly where the call goes to. But management side, you have a pretty nice separation that even is then also good supported for the development perspective.
Okay, cool. Once again, Lera, if you want to follow up on that, please feel free. Now we have a question from David Leitner, who asks, how would you migrate from an existing so-called classical distributed system, SOA, microservices, etc., to an actor system?
Okay, I would say one possibility could be to really look at the problem that you have. So, for example, if you think about having maybe a little bit too big microservice, to think about what is the part of it that really can be parallelized perfectly. So where's the algorithm where you really can span out different work, where you can really take advantage of all the fine granularity into it. And especially if you have things that need different scalability, have different scalability demands. It's really a good idea, same as you also already have on the bigger level, if you think about separating and cutting microservices, to put them into different grains, to really take care what is the thing where the flexibility to work on really independent little things and little classes from a development perspective, you could say, where could it make sense to have them separate out, scale them directly, maybe just have them spawned for a small period of time and then remove them again if you don't need them anymore. So to find the core where this kind of operation really would shine, and maybe start extracting those into a microservice, into an actor-based system. And even you could think of keeping the microservice, and as the core of the microservice, you could use a small actor-based system. And then if you see that demands increase, you could even use it and put them out and scale it even more. Right.
Cool. Thank you for that answer. With an observation question from LET. Aren't actor models and microservices solving different problems? Microservices at the level of organizational scaling and actors at the level of parallelizing computation?
Yes, that is a very good observation because that's effectively what it boils down to.
So I think even if it was not very explicit, but it was also part of this table that you showed here. That's true.
Okay, cool, great. At the moment, let me scroll down there, but I think we don't have any more questions in the chat. Still giving people a few seconds. But yeah, I think it's a wrap then. Thank you very much, Paul and Raphael, for this very interesting insight into actor-based systems.
Thank you for having us.
We're thanking everybody who took the time and listened to this and interested in those topics. And see you the next time.
See you.
See you.
See you around.